This video is about logarithmic identities. Let's first review exponent laws. We know that x to the power m times x to the power n equals x to the power m plus n. The x to m divided by x to n is x to m minus n. If we raise x to the power m and then raise the whole thing to the power n, this equals x to m times n. Then negative powers, x to negative n equals 1 over x to n. If we have a product of two numbers, x and y, x times y to the power m equals x to m times y to m. X divided by y to the power n equals x to n divided by y to n. X over y to the power negative n equals y over x to the power n. Make sure that you are familiar with these exponent laws, because for logarithmic identities, we need to use these exponent laws. Let's see an example. Find all positive values of x such that x times x to the power 1 over x cubed equals x to the power x divided by x. Let's first simplify the left-hand side. We have x times x to the power 1 over x times 3. This is x to the power 1 plus 3 over x. The right-hand side equals x to the power x minus 1. Therefore, we have x to the power 1 plus 3 over x equals x to x minus 1. Now, if x is bigger than 1, then we must have 1 plus 3 over x equals x minus 1. Multiply both sides by x and move all the terms to one side of the equation. We get x squared minus 2x minus 3 equals 0. So x minus 3 times x plus 1 equals 0. X equals 3 or x equals negative 1. We want positive values of x, so x equals negative 1 does not work. We have one solution, x equals 3. This is the situation when x bigger than 1. Now, if x is less than 1 bigger than 0, we'll have the same equation, 1 plus 3 over x equals x minus 1, and there are no solution in this interval. Then we need to consider the situation with x equals 1. If x equals 1, then the left-hand side is 1. The right-hand side is also 1. Therefore, x equals 1 is a solution. So we found two solutions, 3 and 1. Now, let's prove some logarithmic identities. First, prove that log base a b to the power c equals c times log base a of b. Basically, if we have exponent c here, we can bring it down as a coefficient of log base a of b. How do we show this? Let's denote log base a b to the power c as x. Then we know a to the power x equals b to the power c. We denote log base a of b as y. Then we know a to the power y equals b. If we raise this equation to the power c, we get a to the power y times c equals b to the power c. Therefore, a to the power x equals a to the power y times c. A is the base of the logarithmic function. Therefore, a is not 1. A is bigger than 0. Therefore, x must be the same as y times c. In other words, log base a b to the power c equals c times log base a of b. This is x. This is y. This is how we prove this identity. This identity is very useful. It helps us to simplify exponential functions. It brings the exponent down as a linear coefficient. Now, let's see this identity. Log base a 1 over b is simply log base a b to the power negative 1. Therefore, using the identity we just proved, we have negative 1 times log base a b. So negative log base a of b. Now, let's look at the second logarithmic identity, also problem 13.17. We want to prove that if a and b are positive and n is non-zero, then log base a to the power n of b equals 1 over n log base a of b. Let's denote log base a to the power n b as x. Then we know a to the power n to the power x equals b. So a to the power nx equals b. Now, denote log base a of b equals y. Then a to the power y equals b. Because a is positive and a is not 1, this and this tells us nx equals y, or x equals y over n. X is log base a to the power n of b. Y is log base a of b. Therefore, we have log base a to the power n of b equals 1 over n log base a of b. This is how we prove part A. Now, let's look at part B. The left-hand side is log base a to the power n b, then put m here, using the identity we proved on the last slide. Then, using part A, we have m over n log base a of b, which is the right-hand side. This is the end of the proof. Prove that log base a of b plus log base a of c equals log base a of b times c. Let's denote log base a of b as x, log base a of c as y. Then this means a to the power x equals b. This means a to the power y equals c. Then a to the power x plus y equals b times c, which means x plus y equals log base a b times c. And x is log base a b. Y is log base a c. Therefore, log base a of b plus log base a of c equals log base a of b times c. This is how we prove part A. Now, let's look at part B. Evaluate the sum of these three quantities. We have the same base 6. Therefore, it equals log base 6 2 times 27 times 4, which is log base 6 2 cubed times 3 cubed, which is log base 6, 6 cubed, which is 3. Prove that log base a of b minus log base a of c equals log base a b over c. Let's denote this as x, denote this as y. Then a to the power x equals b, a to the power y equals c, a to the power x minus y equals b over c. X minus y equals log base a b over c. X is log base a of b. Y is log base a of c. Therefore, log base a of b minus log base a of c equals log base a of b over c. Prove that log base c of b equals log base a of b over log base a of c. This is a very useful identity. Let's denote this as x, this as y, and this as z. Then c to the power x equals b, a to the power y equals b, a to the power z equals c. A to the power z equals c. C to the power x equals b. Therefore, a to the power z times x equals b. And we have a to the power y equals b. Therefore, we must have z times x equals y, which means x equals y over z. Or log base c of b equals log base a of b over log base a of c. Problem 13.20, Part A. Evaluate log base 2 of 8 times log base 8 of 64. This equals 3. This equals 2. Therefore, this equals 6. B. Evaluate log base 3 of 9, which is 2. Log base 9 of 1/3. 9 to the power what equals 1 over 3. This is 3 to the power 2x equals 3 to the power negative 1. So x equals negative a half. 2 times negative a half equals negative 1. Part C. Use the first two parts as a guide to guess what we might simplify, this and this. Log base a of b times log base b of c. This equals log base a of b times log base a of c over log base a of b, using the identity from last slide. Then this cancels with this. Therefore, we have log base a of c. This is how we prove our guess. Evaluate 4 over log base 10 of 5 minus 2 over log base 4 of 5. This term equals 4 over log base 5 of 5 over log base 5 of 10. So 4 times log base 5 of 10. This term equals 2 over log base 5 of 5 over log base 5 of 4, which is 2 times log base 5, 4. Therefore, the whole thing is 4 times log base 5, 10, minus 2 times log base 5, 4, which is log base 5, 10,000, minus log base 5, 16. which is log base 5, 10,000 divided by 16. This number equals 5 to a power of 4. Therefore, the whole thing equals 4. Evaluate 3 to a power log base 3 of 4. Denote log base 3 of 4 as x. Then 3 to a power x equals 4. This quantity is 3 to a power x. Therefore, it's just 4. A to a power log base a of x. Denote log base a of x as y. Then we have a to a power y equals x. This is y, so this is a to y. Therefore, it equals x. Let's summarize our findings. Log base a b to a power c equals c times log base a of b. Basically, it means the logarithmic function can help us bring the exponent from the shoulder of b to here as a linear coefficient of the term. Then log base a 1 over b equals negative log base a of b. You will see this frequently as well. Then log base a to n of b equals 1 over n log base a of b. This one is a generalization, a combination of the previous identities. So we have a power m here, which can be brought down here. Then the exponent n can be brought here as the denominator. Then log base a of b plus log base a of c equals log base a of the product. If we have a negative sign instead, then we have a quotient. This identity is very useful. It changes the base to the same thing for the numerator and denominator. Log base c of b equals log base a of b over log base a of c. This can be used to prove that log base a of b times log base b of c equals log base a of c. Then we have 1 over log base a of b equals log base b of a. We just exchange a and b. Finally, a to a power log base a of x equals x. Now please pause the video and work on the exercise problems at the end of this section. After you're done, check your answers using the solutions manual, and then continue watching the video. Problem 13.3.6. Prove this identity. Log base a of b times log base c of d equals log base c of b times log base a of d. Log base a of b equals log, we choose any base, let's choose 2, base 2 of b over log base 2 of a. Then log base c of d equals log base 2 of d divided by log base 2 of c. This is the left-hand side. Now right-hand side, we have log base 2 of b over log base 2 of c times log base 2 of d over log base 2 of a. Then look at both sides. The numerator both have this factor and this factor. The denominator both have this factor and also this factor. So these two quantities are the same. This is how we prove the identity. This is the end of the video.